Now that we have been introduced to our home galaxy, the Milky Way, it's time to consider the almost countless galaxies out there in the observable universe. And we'll discover that there are spirals, like we see in this image here, with bright yellow centers. And in this case, we can easily see the spiral structure coming out of that center region. We also have the ellipticals, and they are redder than spirals. They are rounder. Sometimes they're more football shaped, and they consist of very little dust and gas, unlike the spirals, whose dust and gas is clearly seen in the background image here. And finally, we have the irregular galaxies, which are neither disk-like nor rounded. They're odd-shaped galaxies that are a little bit harder to categorize. So we are going to classify the galaxies, consider clusters and superclusters of galaxies, galaxy mergers, dark matter, galactic distances, and the Hubble law. We are fortunate to live in a time where images of galaxies are just quite phenomenal, and there's a lot of them. I'd like to show you a few. So here's a galaxy cluster, S0740, and a giant elliptical shows up here, and a spiral, and many other galaxies interspersed throughout this image. Most of the lights, the dots of light, are galaxies. Hundreds and even thousands of galaxies in an image. Here's 3 galaxies in Draco that show up very prominently. Others are interspersed throughout here as well. But in this particular orientation here, we have an edge-on spiral, we have an elliptical, and a face-on spiral. Let's consider the spiral galaxies. These are the star-forming galaxies. Here we show Pinwheel galaxy M110, a very lovely galaxy. It consists most fundamentally of a thin rotating disk of stars, dust, and gas that we can see here in this face-on image. Spiral arms where the stars are being born. You see all these lit up areas of star formation. Also a central bulge of tightly packed stars, and that bulge merges smoothly into a halo, which is an extended region, very diffuse population 2 stars, and globular clusters that can extend over 100,000 light years in radius. Generally too thin and spread out to be seen, but very prominent nevertheless. There's the disk component. The disk component has stars of all ages, young population 1 stars and older stars as well, orbiting in the disk. Relatively circular orbits around the center of mass of the galaxy, near the center. Lots of interstellar gas and dust in this disk component. And then the spherical components. Old stars with random orbits in the bulge and halo. So you got the bulge, which is easily seen here, the halo, which is not seen, but old stars orbiting those 2 regions. Very little cool dust and gas, so there's not new star formation going on. Here's a very prominent bulge galaxy in the sombrero, seen near the edge on. Pretty amazing galaxy there. Before we go any further in understanding spiral galaxies, let's get this thing called the winding dilemma out of the way. As we investigate galaxies, we notice that the stars, as a function of radius, their speeds are approximately constant. That's not totally true, but let's assume it is for the moment, because they are constant enough that this winding dilemma should manifest itself. And it's a situation that as time progresses, the inner stars, like A here, compared to B, C, and D, that inner star, if it's going the same speed as the outer stars, should orbit quicker. In other words, it should be not in speed, but in period. So as it does a half an orbit, these outer stars haven't gone as far around their orbit. So as time progresses, when A makes 1 orbit, B has got a half orbit here. And what you notice is an increase in the winding of the spiral structure itself. So it tends to wind up. Well, that's what would happen if the spiral structure was made out of fixed stars. If when we look at the spiral arms, they consist of a set of stars that's fixed with respect to time. Well, since we don't observe this, it means that we have the wrong model. And in fact, the stars that make up the spiral arms are not always the same. This will be understood as we investigate what's called the spiral density wave model that will answer this dilemma. As we investigate and observe spiral galaxies, we see generally two distinct flavors, you might call them categories, flocculent and grand design. So as you can see, there's a significant difference. Probably if I asked you to vote for which one you like the best, you'd vote for the one on the right, the grand design. Well, I would too, for that matter. We tend to like those objects that are visually appealing. Well, the flocculent spirals are characterized by fuzzy and poorly defined spiral arms, not really distinct arms here. The stars that are forming compress the gas and trigger new stars, which produce supernova. The shock waves perpetuate that process. The differential rotation of the orbitals of the stars around the center of the galaxy spreads that star-forming region into the arm, which is now highlighted by OB stars. So the OB star formation is revealing the presence of what looks like spiral arms. You can actually see that structure a little bit. The OB stars explode, however, and dim before any winding can occur, as we just discussed. So there's not enough time for the OB stars to live where any winding could be seen. The old arms fade and new ones appear because of this perpetuating process. And the net result of this is that we have chaotic and fuzzy arms that are not real clear, as opposed to the grand design spiral, where we can clearly see distinct arms that are, again, very visually appealing. The stars, as before, compress the gas and trigger new star formation, producing supernova and shock waves, perpetuating the process. But in this case, the arms are molded by what's called the spiral density waves that are being produced, that are modifying the conditions in the arms, and the stars actually go in and out of those arms. This is different than just simply stars initiating new star formation and then tending to wind up the galaxy. So there is no winding issue in this case. No winding issue. The spiral structure stays essentially visually intact. So just to make it clear, this star formation process in the arms is perpetuated by new massive stars that are compressing the gas and dust and initiating the gene's instability, producing protostars, which then become their own massive stars that produce stars in their wake as well. And in this way, we perpetuate the process of star formation through the galaxy. Now, this star cloud compression can also be initiated by the gas clouds themselves colliding and other gravitational instabilities. Star outbursts like nova and supernova that can produce shock waves, producing new stars as well. So the main thing to keep in mind when considering the spiral structure of galaxies is it is not a rigid system. The stars are not fixed in the arms, but they pass through. So the density wave can be visualized when we consider, say, a slow-moving truck moving down the highway, and the cars behind it bunch up behind. And if you looked from above, from a helicopter, you'd see this increased or enhanced density in the region of this slow-moving truck. Now, the whole system is moving down the highway. The truck is part of that density wave pattern, and it's moving along. But the stars are coming in, slowing down, and then passing, speeding up again, spreading out once again. So that's how the stars essentially flow through the arm structure of a spiral galaxy. They get compressed, and then they pass and then speed up again. So at any given point, at any given snapshot in time, you look at the arm, and it's a different set of stars that you see in the particular spiral arm. So it's a self-sustaining pattern because gravity and pressure are working together to slow the stars down as they enter and then speed up as they pass through on the other side. The density pattern itself does not move with the stars, but you could say it travels through the disk like a wave, and that's why it's called a spiral density wave pattern. The really big stars will die out before they have a chance even to pass through an entire arm. So you see an enhanced amount of light, OB star associations in particular, that live and die in the arm. And the stars that actually go completely through are smaller stars that aren't as bright, that make it through an arm and on to rotate around the galaxy more times. So here's a basic spiral density pattern in a rotating system. If you make disturbances in that system, like the truck represents, it doesn't wrap itself up. There's no wrapping effect from a spiral density wave. Check out this wonderful animation of the density wave pattern in a spiral galaxy that can do far more justice than any of my words can. If you look at a particular star and follow it, you'll notice it passes through, a given star passes through a density wave. The density waves are the spirals themselves. There's two prominent ones here. If you observe those spiral patterns, you'll notice it's rotating. It's rotating, but it's rotating at a different rate than the stars are. And then on the edges, you can see the OB, bright young OB stars that are living and dying. Hopefully you're not getting too dizzy observing this. Are you still spinning from that animation? Well, the spiral arms are where new stars are being born. We have the stellar nurseries. Molecular clouds are contained therein. Clusters of bright blue stars surrounded by ionization nebula, the OB star associations, are all there. So here's a somewhat magnified view of a region of the spiral arm in the Whirlpool Galaxy M51. And we see these dark regions where the clouds are packing together. The flow of stars is through the arm in this direction. We have compression triggering star formation. The blue specks that you can see here are the regions of OB stars, and of course lighting up the nebula. And this clearly shows the formation of stars in the arms. Lots of gas and dust, all compressed in the spiral arms, the raw materials for the new stars. Here is Spiral Galaxy M51 in all its high resolution glory. Grand design spiral off the end of the Big Dipper. Notice it interacting with a companion galaxy over here. This is a very, very well-known and beautiful grand design spiral. We have the spiral galaxy in Pegasus, 50 million light years away. The surrounding galaxies are just really incredible in this image. And the galaxy itself, NGC 7331, look at the tremendous amount of gas and dust that's part of this spiral galaxy. We have NGC 4725, a one-armed galaxy, about the size of our own, 100,000 light years across, 41 million light years away. The 1000 Ruby spiral galaxy in Hydra, 12 million light years away, 40,000 light years across. Lots of OB associations in this galaxy. And here we have one of our neighbor galaxies, M33, a spiral galaxy in Triangulum. It's a flocculent spiral. It's the third largest member of our local group of galaxies, 3 million light years away only, 50,000 light years across. And the Andromeda Galaxy, our big sister, M31, 2.5 million light years away, 200,000 light years across, about 500 billion stars, and the most distant object that human beings can observe with the unaided eye. In addition to regular spiral galaxies, whether flocculent or grand design, we also have barred spiral galaxies with a prominent bar structure in the center where the stars are going back and forth. This one is a very stereotypically shaped one, as we noticed from this schematic in the inset. Now, it turns out our Milky Way galaxy itself is a barred spiral. However, it probably does not have such a prominent structure in the center, which in fact has a different developmental history than regular spirals, and it's not very well understood how these form. It might have something to do significantly with the supermassive black hole in the center. Then we have lenticular galaxies, which are strange creatures. Namely, they have a disk component and a spheroidal component. The disk component you can see here with the streaky dust lanes in the disk, and the spheroidal component is pretty obvious, but no arms. So that's a little bit odd. They are somewhere in between spirals and ellipticals, which is our next topic. Among the large galaxies in the universe, most of them turn out to be spiral or lenticular, although the very largest galaxies are in the domain of the ellipticals. Here's spiral galaxy NGC 1097, very strange one. You notice that the center region, the nucleus of the galaxy, is extremely bright, which is most likely the result of this interacting galaxy having gone right through and produced a tremendous burst of new stellar activity in the center, producing this strange, very luminous, and very curious geometrically shaped structure in the center, namely circular. And check out this very high resolution image of a barred spiral, about the size of our own galaxy, 70 million light years away.